So like before, like most of our sections in our book, there is an intro video for all this with explanations of terminologies and parts of antiderivatives and some basic rules.
Video, so I have no idea.
Uh-oh. Well, I would, especially, obviously you can see rules there. Parts of it, definitely a good thing.
I'm not gonna lie, I learned how to do this yesterday in physics class.
That's fine. Did you learn all the rules, like with sine, cosine?
Well, I just go backwards with the sign.
And that's what it is. You're basically asking yourself, what function, if I differentiated it, would be this?
Yeah.
That's what I didn't like about the way they taught it yesterday, because in physics, because they taught like integration, but it did it as like a formula, and it's right with like n plus 1, and then you multiply it by 1 over n plus 1. And that's right and everything, but everyone knows the power rule in there, and it's really not. It's just like it's the reverse power rule, and that was never articulated. It's just like there's like this strict formula, and people are struggling with it. It's like no, just
It's the exact opposite of what you did for a derivative power rule.
yeah. And like if you can teach with like this formula and stuff, but if you can clarify, it's just hey guys, it's just the reverse power formula.
It's about connecting. It's about connecting.
Yeah.
Yep. Connecting what you knew to what you were supposed to learn. Yeah, I agree.
So the negative 2. Because you
Oh, I can split up. Jeez.
I figured out
Isn't
the
that
one.
because like negative sign would be negative cosine?
You just said negative sign would be negative. I'm not sure what you mean. You have to clarify.
Antiderivative of negative sign is negative cosine.
No. I prefer not to think of it. I don't think of it like that. I'm going to think of it as, I'm just going to say antiderivative of cosine is sine, and the antiderivative of sine is negative cosine.
Oh, knew it.
So if there's like, if it's like plus some term or minus some term, I don't get too hung up on what's in front.
Okay.
I'm just going to say, what's the integrand? I'll deal with that. And then if there's some number or sign out front that I need to deal with, I'll deal with that second.
Gotcha. Do we have to do the u sub thing?
Not yet.
That was just if you
I would just, the 2 is a constant multiple. I just get the 2 out of there.
what derivative makes.
I'll show you in a second. I'll show you.
Makes what?
Tan secant.
Outside the integral. You could.
Tangent?
Yep, you could.
Be diligent.
And
I
whether
think
you do or don't do that,
No, then it's
sometimes it's going to feel like it makes a big difference, and sometimes it's going to be like, that made no real difference.
Because is the first one 5½ x squared? Okay, so I did that. Oh, good job, Maggie. I'm so much better.
All right.
What is it? Is it?
Yes, sir, Forrest.
I don't know how to do this.
Well,
This is rough.
let's do this then. Okay. So number one. You've got 1, 2, 3, 4 different terms in your integrand. One of your rules that was mentioned in the intro video is that if you are doing the antiderivative of a sum or a difference, you can essentially go term by term by term. So you won't often see me do this unless it has a real impact on what I'm trying to do. In this case, it might not have a huge impact, but I'll do it anyways, just to illustrate. So you could rewrite this as the antiderivative of 5x dx plus the antiderivative. Now that second term I'm going to tell you right now is currently written as a fraction. We really don't want that. And we're going to talk about fractions later, but for now, if we can avoid fractions, we're going to avoid them. How could I turn this into something that's not a fraction?
X to the negative 4.
There you go. So I'm going to write that as x to the negative 4th dx minus the antiderivative. And I really don't like radicals either. How could I change that from being a radical to something else? X to the 1/2. Yep. Dx plus antiderivative of 2 sine of x dx. So I can split this up into 4 separate antiderivatives. That's really what we're doing. Whether you physically did that on your paper or not, that's really what we're doing. Any questions so far? No. Unless it has a real consequence, like a real impact on what you're trying to do, you don't have to write that. You can just go term by term. So then here's another thing you can do. And again, these two things I'm about to do, these are not huge impact things, but they're things you could do that might have an impact at another point in time. Do you see how the 5 and the 2 they're constants and they're being multiplied by something that's not a constant, like 5 times a variable like 5x, 2 times a variable expression like sine of x. And so what you can do with a constant multiple is you can bring it outside of the antiderivative. So I'll rewrite real quick like this. It would be 5 antiderivative of x dx. There's no constant multiple here, so I would just leave that as is. Same thing with this one. This one, the 2 is a constant multiple, so I could rewrite like so. I don't think that you have to do that. Something you could do that in certain cases would be helpful. How are we doing? Rusty people. Some of you are feeling rusty. Okay, so now what we need to do is we need to go through and identify what is the appropriate method for finding the antiderivative. And I'll tell you, 3 of them are the exact same method as each other, and one of them is different. Which is the different one? Sine of x. And the other 3 are going to involve what strategy? The power rule for antiderivatives, yes. So for the first one, of course it's x to the first. So the power rule for antiderivatives tells us to add 1 to the old exponent and then divide by the new exponent. So 5 times x squared over 2. Then, same sort of a rule for the next one. This would be plus, we add 1 to the old exponent and then divide by the new exponent. So there's our second power rule. Our third power rule would be minus. We add 1 to the exponent, so that would be 3/2. We divide by the new exponent. You'll rarely see me write that step. I'm usually just going to copy dot flop. Whatever phrase you like to use, I'll usually do that right away. And then lastly, the antiderivative of sine is negative cosine. So I'd write this maybe as minus 2 times cosine of x. And we would want to remember to have our plus c in there, that constant of integration right there. I'd clean this up a little bit for a final answer, like maybe 5/2 x squared minus 1/3 x to the negative 3 minus 2/3 x to the 3/2 minus 2 cosine of x plus c. It's a little more presentable. They're both correct. Whatever. You can go either way there. Okay. Is the rust starting to be less rusty?
Sure.
Okay.
Almost.
Yeah, we got a little ways to go. It's fine. Number 2. Number 2 almost feels like I didn't give you enough information, huh? It's like integral of what? Not 0. 1. Yeah, that's true. So it's 1 dx. If there's no coefficient, we understand it to be a 1, right? So if I were to think this through like backwards, kind of like Jack was talking about earlier, if I ask myself, well, what expression if I differentiated it would give me 1? What's the answer? X. So the antiderivative here would be x. And then don't forget the plus c.
Oh, that's a 1.
So it'd be x plus c. All right, number 3. We are not afraid of fractions, but we'd rather avoid them if we can. Any suggestions on how we could do that, Nick? Nick, somehow it's amazing what you do with your voice.
Yeah.
Incredible.
I know, right? I'm split it up into 2 terms. Right? Did I do that?
What do you, so let's,
So like have x over root x plus
okay.
1 over root x.
I got this.
So a little bit different than what some of your classmates did, but you can do that.
I can.
So what you've done, you've kind of like, it almost feels like you jumped out of the frying pan right into the fire, because now instead of 1 fraction, there's 2.
Nice one.
So we still got to deal with the fact that there are fractions. Nick, number 2. Nick's female voice. Meg?
Oh, I heard Nick too, so I was waiting for him to go again.
Sorry, I'm just messing because you were answering for him before. What do you got? What do you think we should do?
Okay. Flip it up. Flip up.
Okay, so you're thinking of like a slightly different strategy from Nick?
Yeah, completely different. Let's ignore what Nick did.
Okay, so
Say it like that.
if I were to take the denominator, and believe it or not, so Meg, both folks have presented a viable strategy. Meg's strategy is probably the more common of the two, but also I would say it's the one that's messed up the most through like just simple stuff. Meg, what would it look like if we actually did flip that up?
Sure. Well, first, in my head, I would probably need to write this down, but I would probably make it x to the 1/2.
Right?
And then I would bring that to x to the
So a lot of people forget the negative in this scenario. So like the way she just presented her thinking was pretty good. That's probably why she didn't forget it, right? Now, kind of like, I said, Nick jumped out of the frying pan into the fire with his strategy. Meg is still kind of in the frying pan because if our integrand is a product, in other words, like something times something else, we are really, honestly, in a similarly difficult situation as we were with the fraction. So if I was going to go Meg's route, I would say, well, take this thing from being a product to being not a product. What would you all suggest? Distribute. Yeah, let's take, you could do substitution. I don't think you'd find that it would work. The numbers would just be ugly. So if I distributed, I'd get x to the 1/2 plus x to the negative 1/2 dx. And then to hopefully bring this full circle with Nick's, if I tried to similarly simplify it, what's x over x to the 1/2? It's x to the 1/2. And what is 1 over root x if we simplified it? Yeah, so plus x to the, look at that, it's the exact same thing that Meg was thinking of. They both took 2 steps. Is one better than the other? That's hard to answer. Listen, as long as you're not like doing anything like mathematically illogical, hopefully the path that you choose makes sense to you and leads you to a good place. So don't think of it as just like a prescription. Think of it as what's right, what's logical, what's wrong. Let's avoid that and get where we need to go. Okay, so you all see the 2 power rules here brought together by these two. So if you did this, you'd get, this is how I'd normally do this. I'd do this in one step. I'd go 2/3 x to the 3/2 plus 2x to the 1/2 plus c. I'm just going to automatically copy dot flop. I'm not going to mess with the something over a fraction. Just instantly copy dot flop. All right, how we doing?
Fantastic.
Fantastic. All right, so we've gone from really rusty to fantastic.
Well, maybe I'm getting ahead of myself.
Okay. So the last one in this little set here, number 4. Let me just do a little switcheroo. This will work. Hopefully,
Switcheroo, huh?
there we go. It's a highly technical term.
Works there.
All right. Does anybody have a strategy that you think might work with number 4? Because it's got trig stuff in there. It's a fraction. Anybody come up with anything good for number 4? Yeah, Logan, what do you got?
I converted it into tangent x times secant x.
Let's show one little step in between, but I like where you're going.
Okay.
Oh, that's
Could you not do this? Maybe like sine of x over cosine of x times 1 over cosine of x?
Correct.
And then, of course, your next step would be what Logan said to begin with. I think makes a lot of sense. Okay, so antiderivative of tangent of x times secant of x. We do a little trig identity. It leads us to a good place. What do you think the result is?
I forgot what, so I kind of took a stab at it, but isn't it the derivative of secant x?
Yeah.
yeah, you did.
So secant of x
Bring it in, Logan.
plus c.
What did
So I like the way Logan expressed his thinking. He said, wait a minute, isn't tangent of x times secant of x, isn't that just the derivative of secant? So the antiderivative of that would then have to be secant, right? So it's really good reasoning. So I like it, and you happen to remember. So all the better. All the better. What do you guys think about 1 through 4? Plenty of things to navigate there.
Yeah, that was great.
Can you tell, even if you were an AB veteran and you did really well last year, you need to practice a little bit, right?
No.
It's in there. You know that it's in there somewhere. You just got to get it back out, right? You got to bring that skill back, and you'll be okay. If you wouldn't mind, please try numbers 5 through whatever it is, 7 or 6. 6. Try 5 and 6. See how it all goes. I'll get these up on screen. Here's 5 and 6. 5. So did you guys do something similar to what Nick and Meg were talking on that one earlier?
I did do what Meg said to do.
So maybe you did this.
Meg is awesome.
And I think either one of them works great, but maybe you did 2x squared minus 3x plus 5, and maybe you flipped up the denominator to the top
Yes, sir.
and got that. If you did do that, realize that a product is really no more helpful than a quotient. It really isn't. And so you'd have to take it from this over to being not a product either. And here the distributive property would be the key. So you'd end up with the antiderivative of 2x to the negative 3 minus 3x to the negative 4th plus 5x to the negative 5th dx. Make sense? Now we just go term by term.
I was like, what are you talking about?
So I'd say a final answer would be negative x to the negative 2 plus x to the negative 3 minus 5/4 x to the negative 4th plus c. I think I did all my addings and subtractings correctly. Peyton, I do have to slow down to make sure I don't mess that up, right? It happens. We know that. Okay, questions on that one, number 5. Okay, so we were talking about number 6 up here. Veterans especially, would you guys agree with me that with number 6, isn't number 6 very dependent on the idea that you recognize that secant squared is like something special?
Yes.
You'd have to look at that and say secant squared. That just seems so random. Why would that be in there? Oh, wait a minute. Secant squared is the blank of blank. Right, and so the antiderivative of that would have to be tangent. So you'd end up with 4 times tangent of x plus c. And hopefully you'd feel good about that because you're really good at derivatives. Yes? No? Maybe? Okay. All right. Good deal. Any questions, follow-ups there? All right, let's roll on. We're doing good. Yes. So,
Look at that distance.
so beautiful. Yes. Okay. So, one of the common themes I would say that will run through much of our class is differential equations. How do you get them? What are they? How do you solve them? That kind of thing. And so it's fairly September. We're going to start it now, and it'll just continue to weave its way through most of the class. Most topics, we'll see stuff like this. So let's talk about what these are. A differential equation is an equation with one or more blank. Anybody know what goes in the blank? And I would be willing to accept that because you may not have ever seen this before. Veterans, what makes a differential equation has a what? Depends on if we have the initial condition or not. So that may or may not be true.
Variables?
They'll all have variables. Be more specific. What?
That's good stuff. Constant. It's critical points.
More than one constant, more than one.
Not critical points.
No, it can have
It may or may not have
The
a
washer
constant.
method. What now?
x value, integral, antiderivative,
Oh, so
Endpoint. Maxima.
minimum, relative inflection point.
you guys are all just thinking of all the wrong Sunday school.
We literally said integral, but we didn't think of
Yes. Yes. So these equations will be equations where a derivative has already been done by someone else, and then we do stuff with that, right? So differential equation has one or more derivative in it, and these can be very simple, they can be medium difficult, they can be very difficult. In fact, there is an entire college class called differential equations, in which you study all kinds of crazy differential equations and how to find solutions, or if a solution has even been found. Some people, for their doctorate in math, will spend like 3 whole years figuring out an analytical solution to a differential equation, and they'll spend the 3 years like developing and proving what their conjecture, and then people will try to attack them and say that's wrong. And that
Imagine having 3 years.
people that like design the system that your cell phone runs on, like people that are very good at math, would do stuff like that. So
I want to do that for
doing that.
Shout out to Steve Jobs for this.
What is doing that?
All right, Pete.
to have really good, highly technical jobs, you have to be a very good analytical thinker. Anyways, so let me just take you through some thoughts on how we do this. What tool would we use to undo a derivative or part of a derivative like a differential? Just say it.
Integral.
Or an antiderivative, right? So
I suppose.
yeah, we'll probably call them antiderivatives in this case. If an initial condition is not given, this is just terminology stuff, the answer to your differential equation will be a blank solution. We'll play a little Wheel of Fortune here. Yeah, there it is, general. It's a general solution, and that'll be characterized with a plus C, right? It'll be something or other X with some other stuff, maybe plus C.
What do you mean by initial condition?
So an initial condition is going to be a point that's actually on the solution curve. So I would say in our one example here, this f of 1 equals 0. We would call that an initial condition. or an initial value, because we know that when x is 1 on our solution curve, y is 0. So we know for sure at least that point's on the curve, and we don't know much else yet, but we know that, and so we call it an initial condition. If an initial condition is given, the answer will not be a general solution with a plus c. It will be called a...
Specific.
Hey, that word's even right there. Particular. Specific seems to make sense, but the word we use is particular solution. And we will be finding both in our class. We will be finding both. Okay. I want to show you and remind those of us that might be a little bit rusty the appropriate way of dealing with a differential equation. And there's more than one way to do this. I want to show you the way that will, kind of the pattern, the algorithm that will always allow you to show what you know. And we all know that you want to score well on your quiz or your test or the AP test or whatever it might be. And so it's always a shame when you do good stuff, but then you don't communicate it very well. And then the people that grade your test are like, well, I really can't tell if they know what they're doing because the communication was mediocre or terrible. I want to show you really good communication. Make sense? So here we go. I've got this differential equation. How do I know that this thing right here is a differential equation?
What?
Because differential equations always have...
They got a...
From 3 minutes ago...
They have one or more.
It's a derivative.
There's a derivative in that equation.
Yeah, there's a derivative.
Look, do you see that?
That's just like tight,
little prime.
my dudes.
Do you see that little prime thing right there? Yes.
Oh, I know exactly.
So there is a prime in there, which is a great indicator that there is a derivative that is part of this equation, right? So the first thing I would do is I would retranslate this into Leibniz's variables instead of Newton's. And so it would look like this. I would just write dy dx equals x to the negative 3. And if you wanted to make a little note up here and say, for me, y equals f of x, that's fine. But I would convert over to Leibniz's notation. Now, I'm going to rely on you guys, veterans, a little bit here. What is that one key step that shows that you understand the process of what you're actually doing here?
Separation of variables.
And this is the gateway to credit. Yes. What I'm going to do is I'm going to multiply both sides by dx. And technically, we sort of can't do this. This is just an algorithm to help us establish what we're really doing.
Wait, wasn't this in chapter 3?
It was on that one.
It was on the left side.
Don't worry about it. Let's stay focused on this for the moment. Okay, so you do a little canceling and such, and wouldn't you get dy equals x to the negative 3 dx? Separate the variables. You see all the x's are on the right side and all the y's are on the left side? Okay. So once you've separated the variables, there's another step. We want to get rid of those differentials, those derivative things. We do that, right? The tall, skinny s. We do an antiderivative to both sides. And I'm hoping, based on the example we did a couple minutes ago, what do you guys think the antiderivative of dy would be?
Why?
Why?
Oh, that's just nifty.
Pretty convenient. The antiderivative of x to the negative 3. Just a power rule, right?
Negative 1/2 x to the negative 2.
And then we customarily will put the plus c on the right side over there with the independent variable. Does anybody have a question on that?
No, sir.
Well, let me ask the question that sometimes people will ask. Maybe you're thinking this and just didn't say it. Sometimes people will say, well, wait a minute, why isn't there a plus c over there? Because we did do an antiderivative on the left side as well as the right side. Why wouldn't there be a plus c over there as well?
Because then they would cancel.
Oh, interesting. Interesting. Okay, so let's talk this over. Would we know for sure that those two c's are exactly the same c?
No.
We would not, because one of them is based on y and the other as an integrand. The other one is based on x as an integrand. So there'd be two potentially different c's. And if I've got some unknown c on the right side and then some other perhaps unknown c on the left side, if I were to combine them, what would I get?
C.
Some other c, right?
And that's that.
And that's what that c on the right side is. So that's why we will customarily just write the c with the independent variable. Although if you wrote it over there with the dependent variable, as long as you, bless you, as long as you handle all the details correctly, you'd be fine. You would. Okay, so this is what we call a solution. And because there's a plus C, it's what kind of solution? General. This one asks for the particular solution. So I got to keep going. Here's how I do this. I need to show that I've used my initial condition, which is right here. So this basically means when x is 1, y is 0. So I would write 0 equals negative 1/2 times 1 to the negative 2 plus c. All I'm doing is I'm plugging in the 0 where the y's are. I'm plugging the 1 in where the x's are. So don't overcomplicate that. It's simply input-output. This will allow me then to solve for c. And what doesn't this give me 1/2 equals c? So therefore, my final particular solution would be y equals negative 1/2, x to the negative 2 plus 1/2.
Well, that's pretty cool.
I think the c is positive 1/2, right? Because you'd add that over to the left side. Just, I had to stop and think about it too, so give yourself a break. Yeah. So this would be the equation that contains the initial condition where if you differentiated it, you'd get your original differential equation. I would put this one in the super easy category of all the things we'll do this year with differential equations. And it makes sense, right? Because this is the first one we're doing this year, right? So it makes sense we'd start off with one of the easier ones. So I hope this made sense to you. We'll keep building as the year goes on. We'll keep building more and more into this. But you got to know some more derivatives and things to go along with that. So any questions? Got one more thing to talk about, I think, and then that's it. All right. I think this will go well. So if you would, flip ahead to this. I want to do a couple of fill in the blanks here for you, and then I'll give you a chance to try this one. As far as motion goes, the derivative of a position function is a what function? It is a velocity function. I agree. And the derivative of a velocity function would be the rate of change of velocity. Acceleration. So if we reverse this and we were doing antiderivatives and integrals instead of derivatives, what's the integral of an acceleration function?
Velocity.
Some kind of a velocity function, yeah. And how about if you did the integral of that? Back to a position function, yeah. So hopefully you can see kind of the cyclical nature of this, or the undoing nature of this, I suppose. So the example here, baseball is thrown upward from a height of 2 meters with an initial velocity of 10 meters per second. Determine the maximum height. Physics people might instantly turn to a kinematic.
Yeah.
We will not. I'm going to start you off with one thing. Once the ball leaves this person's hand, other than wind resistance, which as you know in physics, we pretend like wind resistance is not a thing, even though it is, we'll similarly pretend here. So once the ball leaves this person's hand, what is the only force acting on this ball?
Gravity.
And gravity in metric is?
Negative 9.8.
Yeah, so we're going to say that negative 9.8. And what kind of a thing is gravity? Is it a position? Is it a velocity? Is it an acceleration? It's an acceleration. So we're going to start off with acceleration equals negative 9.8. That's the only thing we really know other than the couple of initial conditions up there. So I want to see if you can take those ideas that I've just written up there with the velocity and acceleration position, see if you can work backwards to find the max height of the ball. Oh, is there any information that would help me find my C?
The initial velocity of 10 meters.
Yeah, and what does initial mean?
At 0.
When t is 0, right? Yeah. So that means when t is 0, v is 10. So I could say 10 equals negative 9.8 times 0. I'm showing where I used my initial condition. This, of course, leads me right to the happy fact that 10 is c. Therefore, my real velocity equation in particular is that. V equals negative. I lost my negative in there somewhere. Sorry. Negative 9.8 t plus 10. So we're so good? Okay, so baseball's thrown upward, so I'm going to say that the position is like a Y. You could put P for position or something. That's fine. I was going to say velocity is really dy dt because it's moving upwards, right? Ball's going up. So I'd separate my variables again. And when I did that, I would get dy equals negative 9.8 t plus 10 dt. T's on one side. The other variable on the other side, in this case that's a y. This is where I do an antiderivative. So I'd get y equals negative 4.9t squared plus 10t plus c. Now at this point you might have already figured things out. What's my c going to be? 2, right? Because I already know initial means when t is 0, the height is 2. So you could say y really equals negative 4.9t squared plus 10t plus 2. And that would be my position or my height function. You could have used, did anybody use h for height? That would have made sense as well. Yeah. Okay, so it wants to know the maximum height. So here's, I love the divergent ways of thinking that are actually convergent ways of thinking. A physics student, correct me if I'm wrong, is going to say, well, the max height will happen up there at the top, and that's where the velocity would have to be? 0. And so they'd say, well, when is velocity 0? Then they would take this over here and they'd say, all right, when is velocity 0? They'd go 0 equals negative 9.8t plus 10. They'd solve that and they'd get t equals 1 point something.
0, 2, 0.
0, 2, 0, fair enough. And they'll say, all right, well then I just take that 1.020, I make that my t and my position function up here. And I get y equals what?
7.102.
Okay, that's what a physics student would do. Now a calculus student would say maximum. Maximums happen at critical points. And critical points would be when the derivative of whatever we're dealing with is 0 or doesn't exist. So let's find the derivative. What's the derivative of height? Oh, it's right here. This is y prime, is it not? And they would set that equal to 0 and say, well, I found my critical point is 1.020 equals t. And then they would plug that in. Maybe they'd do what if they did a justification? Could they use the second derivative test? What's the second derivative of position?
Acceleration.
Oh my gosh, and look at that. The second derivative is always negative, so position is always concave down, so you're going to have a max, right? So even though a physics student would maybe use some different thinking than a calculus student, aren't they really doing the exact same thinking? They're doing the exact same thing.
Nifty.
So you'd still get the 7.102. The calculus student may be a little more rigorous and say, well, yes, indeed, what goes up must come down, and we know that based on the second derivative, right? We could justify ourselves a little bit differently than a physics student would, but we're doing the same stuff. Okay. There is an intro video, but it's not for tomorrow. It's for Friday, right? You're going to want to do that. So the intro video for Friday is going to start to get into Riemann sums and area. Riemann sums and area. You guys can tell they're lovely. They're very symbol heavy, but they're pretty simple. Basically, can you find the area of a rectangle? And if the answer is yes, I know how to find the area of a rectangle, you'll be in good shape. All right. Don't forget your test is tomorrow. Have a great day.